Section 3. So last week I kind of mentioned Newton's second law before I should have, I suppose, but call it a lead up. Anyhow, Isaac Newton in the 1680s published his three laws of motion, among other things. We're going to look at the first two in this unit, and the third law is something we're going to save for another day in the not too distant future. But the first and second laws kind of go together. So taking things what might seem like out of order, the second law, well, basically it says forces cause acceleration. If you've got a soccer ball sitting on the ground in front of you and you apply a force to it with your foot, the ball will pick up speed as you are doing this. It turns out, we'll just present this as an experimental observation. It turns out that the amount of acceleration is directly proportional to the amount of force. If you push twice as hard, it picks up speed twice as fast. If you push 5 times as hard, it picks up speed 5 times as fast, and so on. The proportionality constant between these two things is a property of the object called its mass, which I suppose one way of trying to explain the word is to call it the amount of matter that the object contains. It's the way you measure a body's inertia, where inertia means an object's tendency to keep doing whatever it's already doing. Say you're in the grocery store and you've got 2 shopping carts. One of the shopping carts is empty, and the other one you've piled as high as you can with frozen turkeys. It's probably pretty much common experience that the fuller you get your cart, the harder it is to push it. Okay, if you've got these 2 carts and you push on one of them, you're standing in between them, and you push on one with your right hand and you push on the other one with your left hand, and you're careful to push equally hard, you're going to find that the empty cart picks up speed much more rapidly than the one that's much more massive because of all the turkeys in it. Likewise, if you're standing there and both of these shopping carts are rolling down the aisle toward you at, let's say, the same speed, and you stick out, you know, one's going to pass on one side of you and the other one's going to pass on the other side of you, and you stick out your hands and try and stop them, you're going to find that the empty shopping cart is a lot easier to stop. The full one is going to want to push your hand out of the way and keep on going and maybe slow down a little bit in the process. So this tendency of an object to keep doing whatever it was already doing. If it's sitting still, it wants to keep sitting still. If it's already in motion, it doesn't want to slow down or speed up or anything. And that tendency for the velocity to keep the same is called its inertia. The more mass an object has, the more sluggish it behaves, the more inertia it has. If F equals ma, you can divide both sides by m, and it becomes a equals F over m. And we see here, for a given amount of force, if F is a constant, what you've got is an inverse proportion between acceleration and mass. If mass is a big number, acceleration is a small number. If the mass is a small number, the acceleration from the same force is going to be a lot bigger. So the resistance to acceleration is what mass measures, inertia. Summation of the forces, this symbol here is the mathematical symbol for a summation. It means to add. When people say F equals ma, they don't mean one particular force is equal to m times a. They mean add them all, and the total is equal to ma. Okay? Like if I'm pushing an object across the page here, it's not the force from my finger that equals ma. Because you see, at the same time I'm pushing in that direction, this tape dispenser is dragging against the paper, and there's a friction force that points the other way. The resultant of these two forces is what equals ma, okay? And if I'm just pushing it along at a constant speed, sort of like this, those forces are equal and opposite. Maybe I've got half a pound this way and friction's half a pound the other way, and the total is 0, which is why the tape does not accelerate, okay? So the vector sum, that's one of the reasons for getting into all this stuff about vector arithmetic. The resultant of all the forces is what's proportional to the acceleration. Now, Newton's first law is actually not a separate idea from the second law. If Newton was publishing his work today, instead of, something close to 350 years ago, it might very well be Newton's 2 laws rather than Newton's 3 laws, with this thing just being a corollary to the second law. The first law is just the special case where like when I was just pushing on that thing just now, that was actually Newton's first law I was illustrating. The total of all the forces was 0. Therefore, it follows from F equals ma that if this is 0, then that has to be 0. In other words, in the absence of a net force, the velocity does not change. No acceleration, constant velocity, two ways of saying the same thing. Constant velocity means the object not only keeps a constant speed, but also follows a straight line. The velocity is a vector. Both its magnitude and its direction will stay the same unless a force acts to change them. Probably the reason for stating it as a whole separate idea, even though it's not really a whole separate idea, it's just a special case of this idea, is it's historical. As you go through the 1600s, as you might be aware if you know anything at all about the history of science, there was quite a debate going on. By Newton's time, it was getting fairly settled, at least among the intellectuals of the day, but especially in the early 1600s, back in the time of Galileo, because what we call Newton's first law is actually due to Galileo, okay? Not to belittle Newton. Newton was a seriously smart guy, the kind of person who, because he needs it for something else he's working on, sits down one day and invents calculus, okay? But what Newton did was able to take the isolated discoveries of the various people who had gone before him. Galileo discovered this, Kepler discovered that, Descartes did a little some things, and so on and so on and so on. And he was able to take all of those sort of standalone discoveries and weave them all together, along with some significant discoveries of his own, like universal gravitation, for example, weave them together into a complete, comprehensive picture of how the world works, or at least the world of mechanics. Electricity was a topic that had to be left for a different century, but anyhow, this particular piece of what we now call Newtonian mechanics was actually due to Galileo, some 60 or 70 years before Newton was, published his book. So one of the big questions was the structure of what we now call the solar system. As you know, it had been believed for many centuries that the Earth was the center of everything. Okay, you had a system like this where there's, incidentally, the ancient Greeks more than 2,000 years ago knew the world was round and actually had done a pretty good job of determining its diameter. So there's just no excuse for those people today who are trying to tell you it's flat. But you had the Earth at the middle, and you had the various planets going around the Earth. I believe they figured that, well, let's see, where did they have the moon? Well, it doesn't matter what order they were in. It's all wrong anyhow. Well, along comes Copernicus in the 1500s, Nicholas Copernicus, and he goes, a couple of things would make a lot more sense if it was the sun in the middle and the Earth was one of the planets going around the sun instead of the other way around. And at first, nobody paid too much attention. But as the years went by, some people, it got to be a big controversy, and Galileo ended up in some trouble. And you might want to look that up because that's kind of an interesting story. But anyhow, one of the arguments for why the Earth could not be a planet was, another thing Aristotle believed, aside from that, this geocentric model for how the world is set up, another thing he believed was that for an object to move, there has to be a force acting on it. Okay, so there's a little box of staples sitting here too. Aristotle would have said, now look at this. If being at rest is the natural state of this little box, if I want it to move, I have to disturb its natural state by applying a force. And when I stop applying the force, it returns to its natural state. And that's what people believed up until the 17th century. But along comes Galileo, and he goes, and of course, several decades later, Newton looks at what Galileo said, and he goes like, well, yeah, of course. Makes it into his first law. But Newton would have said, now, or Galileo, either one of them, would have said, now watch very carefully. When I stop pushing on the box, it doesn't quit moving immediately. See, my finger came off it there, but it slid until it got over here. If the page had been slipperier, like if I rubbed wax all over it or something, it would have slid further. And, if you take that to sort of a logical extreme, if I could somehow make the surface completely slippery, it wouldn't have slowed down at all. See, the ancient Greeks did not think of friction as being a force in the same sense that pushing something with your finger is, but the more modern point of view is that that's exactly what it is. As I go sliding this thing along, got a force that way, got the friction force the other way. So this is the case where there is no force, no total force. And therefore, in the absence of a force, it keeps moving. Well, one of the questions in the early 1600s, one of the arguments against the Earth being a planet was that even back then, they knew the sun was really far away, so that if the Earth went around it once a year, it had to be moving at thousands of miles an hour. This was at a time when 30 miles an hour was thought of as a terrifying rate of speed. So if the Earth was streaking around at this tremendous rate of speed, clearly any loose objects, you, for example, would get left behind. And since you don't find yourself floating around watching the Earth disappear off into the distance, you know, what was Copernicus thinking? The Earth moves? Get real. Well, Galileo's answer would be, you keep moving simply because you're already moving. The idea of, I mean, gravity has something to do with it too, but gravity was an idea that was still several decades in the future at this point. But you know, even if you take gravity out of it, if you picture yourself sitting on some silly little asteroid that's got a diameter of 10 feet, okay, there is not enough gravity there to be worth talking about. I mean, if you get the hiccups, you're going to launch yourself into space off of this thing. But as long as you don't get the hiccups or make any other sudden motions, you will sit on that little miniature planet as it orbits around the sun at thousands of miles an hour. And you will stay on it simply because you're already moving, and therefore you continue to move. So what we now call Newton's first law was all tangled up in some pretty prominent questions at the time. So he probably stated it in a prominent way because of that. Having laid down a little bit of background now, we're in a position where I can properly explain how our system of units works. So first of all, you need certain standards. You need definitions for a small number of so-called base units. If you go back to when the metric system was originally devised, the metric system is one of the better outcomes of the French Revolution. Okay, some other stuff happened that, yeah, maybe if the French had to do it over again, they would have done it a little bit different. Like maybe they wouldn't have chopped off so many people's heads and that sort of thing. But the metric system was definitely one of their, they were having a good day. So they came up with, well, let's see, what do we want to use for a unit of length? Hey, let's make the distance from the North Pole to the equator exactly 10 million meters, or 10,000 kilometers, if you want to look at it that way. And let's make the mass of 1 cubic centimeter of water, we'll call that a gram. And so there were originally these definitions for these types of units. Well, as you come on through the years, the definitions got revised. The original definition of the meter that I described, the problem with that is if you want to really do a good job of calibrating your instruments, you have to go out and measure the Earth. The Earth is big, and you know, you don't want to have to send out a polar expedition every time you want to do that. So what seemed like a better definition is they got a metal bar made out of some alloy that, you know, platinum and stuff like that, that wouldn't corrode and have pieces of it flake off and all. And they put it as accurately as they could based on the old definition. They put a couple of scratches on that, 1 meter apart, and the definition of the meter became the distance between those two scratches on that metal bar. And that was the definition of a meter for more than 100 years. And well, there's a couple of problems with that definition. I mean, it was better than the first one. But first of all, if you live in New Zealand, you have to go to Paris to calibrate something against that bar. And so it'd be kind of nice to have a reproducible standard that anybody with the right equipment could use instead of having to go where that particular artifact is. And maybe at least as important, what if that bar had gotten blown up during World War I? where would you be then, you know? So another reason to have a reproducible standard that anybody with the right equipment could use instead of basing it all on a specific object. So there was another definition that was in place for a few decades, but the current definition is in terms of the speed of light. Okay, actually, if you want to explain things in a logical order, I should have started with the definition of a second, which of course originally was defined in terms of the rotation of the Earth. A certain number of seconds equals a day. The current definition of the second is based on some atomic vibrations. It gets into how an atomic clock works. Once you have a definition for the second, you can then define the meter based on the speed of light. Okay, so the speed of light is no longer a measured quantity. Rather, the speed of light is defined to be exactly this. Rather, I mean, if they had to do it over again, they would have probably made it 300 million even instead of this number that's really close to 300 million. But, you know, had to be consistent with the value of the meter from the previous definition. So you can, with modern electronic equipment, you can measure the speed of light really, really accurately, like many, many significant figures. And also with modern equipment, you can measure time really specifically, or really exactly. And so the meter then is based on the speed of light. It's the distance light travels in a certain very short fraction of a second. And the SI system altogether has, I believe it's 7 different base units. You need one for electric charge and one for temperature. But as long as you're studying mechanics, which is the branch of physics we're in for the time being, you just need 3: the meter, the kilogram, and the second. Okay. Now, the units for anything else that we're going to talk about for the next probably month and a half or 2 months are based on just those 3. Like, for example, if you want a unit of speed, well, they don't have some artifact near in a little room near Paris, which is bouncing back and forth between the walls at a certain speed, and the speed that's moving is our basic unit of speed. Rather, the unit of speed is defined as a combination of other units instead of based on some sort of fundamental experiment. Likewise, with a unit for acceleration, it's a combination of other units. So then that brings us to, what are we going to use for a unit of force? Well, let's say you had a mass of 1 kilogram and you're pulling on it in a way that makes it accelerate at exactly 1 meter per second per second. Here's maybe a string pulling on it. It's creating a force F. And the question is, how much force would that be? Okay, the SI system defines mass based on a certain experiment. The kilogram is defined now based on measuring Planck's constant. The second is defined, meters a second, I already talked about that. What are we going to use for a unit of force? Well, force is equal to mass times acceleration. If you've got a mass of 1 kilogram accelerating at a rate of 1 meter per second, well, as I've said before, units can be manipulated using the same rules of arithmetic that you use with numbers. This would be measured in kilograms times meters per second squared. And so that is the SI unit of force. Just like meters per second, and just like the unit of velocity and just like the unit of acceleration, it's defined as a combination of other units rather than based on some sort of experiment, okay? there's just one thing wrong with this. It's just a terrible name. Kilogram meters per second squared. Nobody wants to say that. Oh, my diet is working really well. I've already lost 20 kilogram meters per second squared. That's just not going to catch on. So let's give this combination of units a name of its own. And since we use Newton's law to come up with it, it seems kind of appropriate to name it after him. Most SI units are named for people, okay? There are a few exceptions. There was never any Bob kilogram or anything like that, but in most cases, they've been named in honor of what seemed like an appropriate person. The watt is named after James Watt, and so on. So that's what a Newton is really. And why should you care? Is this just a bunch of obscure trivia that matters only to people who are really deeply involved in weights and measures? And the answer is no. This is something you need to understand if you want to avoid the dreaded red pen when taking your physics test. Because one of the things I use more red ink on than just about anything else is, for example, let's say instead of calling that, let's say I put a ridiculously simple question on a test. Don't expect to get something like this for real, but what if instead of calling that a kilogram, I called it 1,000 grams? It's the same thing. I told you that that was accelerating at 1 meter per second, and said, okay, what's that force? And you said, oh, this is an easy one. F is equal to m times a. And so 1,000 was the mass, and the acceleration is 1. And so that force is 1,000 newtons. No, it's 1 newton. Now, you might look at this and say, oh, it's only a decimal error. Well, yeah, I'm waiting for one of my paychecks to come out with the decimal point 3 places further over from where it belongs. It'd be pretty tempting to find a country that does not have an extradition treaty with the United States to, I mean, anyhow, you need to understand all this stuff about units to avoid these kinds of, well, in the case of the SI system, they're always decimal errors. You get into traditional units and it's like, you know, forget to convert inches into feet, you're going to be off by a factor of 12. But in the metric system, it would always be a decimal error because everything is just moving decimal points. But you have to keep in mind that for any kind of calculation, if you're going to get the standard unit out, you have to be putting the standard units in, okay? Since a Newton is a kilogram meter per second squared, if you expect it to come out in newtons, you have to put in kilograms. Grams is no good. Here, I didn't feel like digging around all day to find the formula sheet for your class, but this one is very similar in that on the last page, it might be page 7 on yours instead of page 8, and a few of the entries might be a little different. But there is a similar table of units on the last page of your formula sheet. Remember, this is the thing you get to look at when there is a test. So if you're confused at any point, you can look this up. I've got this column here that says standard SI unit. So right there is where it tells you that if you've got this question here, that needs to be in kilograms, not grams, okay? So right there is the standard SI unit for Well, for everything these people are going to encounter in that course, and it's almost the same. Bottom of the page also has all of these standard SI prefixes also, you know, kilo means 1,000, and some of the more obscure ones. Zepto always sounds to me like it ought to be one of the Marx Brothers. But anyhow, that is why it's worth raving on and on like this about the units, is because it's because of that thing. You don't want to be telling me something is 1,000 newtons when it's only 1 newton. So for the units to work correctly in a calculation, if you're given grams, you have to convert to kilograms. If you're given centimeters or kilometers or something like that, you have to convert into meters, whatever it says in that column for standard SI unit. Another thing to be careful with is the difference between force and mass. And where this comes from is, you know, in everyday experience, people go around saying, well, this many pounds equals that many kilograms. And technically, no, it doesn't. Technically, asking how many pounds in a kilogram is sort of like asking how many hours in a gallon, or how many acres equals a mile per hour, or something like that. They are units of two different things, technically. A pound, well, here, again, this is the one that I happen to have handy, but yours would look very similar. I phrased it very carefully. For mass, I didn't say, well, quite often you'll hear it said a kilogram equals 2.21 pounds. That's assuming G equals 9.81, which is the mean value for the Earth as a whole, because it varies a little bit locally. Here in Batavia, actually, it's a little closer to 9.80. So based on that value for G, it would be this much of a pound, which is kind of my point. I didn't say 1 kilogram equals 2.2 pounds. I said 1 kilogram weighs 2.2 pounds around here. If you're on the moon, a kilogram weighs roughly 0.4 of a pound, okay? Because a pound is a unit of force, not, so you go down a couple lines. Here's the one with the equal sign. A Newton equals a little bit less than 1/4 of a pound, okay? So don't mix them up with each other. If you get into traditional units, which we're not actually going to use this in this course, but just in case you're wondering, in the foot, when you're working in feet and pounds and seconds and all that, mass is measured in a unit called a slug, which would be the mass of about 1/32 of M equals, yeah, be around 1/32 of a pound. M equals F over A. So anyhow, the reason that people can go around saying this many kilograms equals that many pounds is because you don't take it to the moon, okay? And if the object you're talking about is always going to be in the same gravity, then then that amount of mass will always equal the same amount of weight. But the other factor in an object's weight is the strength of the gravitational field it's in. And if there's a difference in the gravity, the same amount of mass will equal a different amount of weight. So be careful not to mix them up, because again, Another popular place for this thing, if I give you an F equals ma problem, and I tell you, okay, this box is sliding down the ramp, and I want you to calculate its acceleration, and this box weighs 20 newtons. There's always people who want to stick the 20 newtons in for the mass. No, that was the weight. And it's the other way around also. If I tell you, okay, this box is sliding down a ramp, and that's a, I don't know, a 5 kilogram box, then there's always somebody sticking in 5 kilograms for one of the forces on it. Forces are measured in newtons, kilogram, and you can look that up on that table I was just showing you. Kilograms are mass. So be sure not to mix up units of force and units of mass. Mass and weight are not the same thing. Yes, for casual conversation. I even hear physicists use the word interchangeably sometimes, but in just casual conversation. But when it comes to getting the right answer, you got to put in the mass for M, you got to put in the weight for W, and if you mix them up, it's going to be kind of a train wreck of a grade on your paper. So, mass and weight. Mass, as I said, is how many turkeys you got in the shopping cart, okay? Weight, on the other hand, is the force of gravity. Those turkeys will only weigh 1/3 as much if you have them on Mars. The relationship between the two? Well, let's take Newton's law and apply it to a freely falling object. So if you drop a frozen turkey out of a second-story window, here it is on the way down. Hopefully I'm not offending any vegetarians. Let's make it some celery. So if you drop a stick of celery out of a second-story window, here it is on, I know it looks more like a turkey than a piece of celery, but there's its weight. So assuming it's a free-falling object, there's the only force that acts on it. Summation of the forces on this object is equal to its mass times its acceleration. And you look at the picture, well, it's a pretty quick sum when there's only one thing. It's like add the following numbers, 7. The total is 7. And this is the only force. So that's the total of all the forces. Now, this symbol G stands for the acceleration of a free-falling object, which is what this is. So A is equal to G in this case. And so there is the relationship between weight and mass. Mass times the gravitational acceleration equals the weight. Now, if something is not free-falling, like here's my box of staples again, if you were looking at it from the side, there it is sitting on the table. What I want to do is caution people not to confuse this with that. Another thing, not quite so common, but I definitely see it, another thing that brings out my friend the red pen is people just sticking in 9.8 everywhere they see the letter A. Like they're writing an English paper and they get to, this character was and they put in 9.8 for the A. Well, I might be exaggerating a little bit on that one, but if you've just got a box sitting on a table, A equals 0, okay? And the net force on it N for normal force. I'll explain that. That's coming up, but why I've used the letter N for that. But for now, let's just say that's that's the supporting force from the table that it's sitting on, okay? So the letter A stands for what the acceleration actually is. The letter G stands for what the acceleration would be if you dropped it, okay? This force cancels that force, so the summation of the forces is 0, and its velocity is not changing, and so the acceleration is 0, okay? But over here, here's something you've dropped. Based on considering that, we figured out that this force is equal to m times g, and this force is still equal to this even when it's sitting on a table, because it's, you know, it's still the same amount of mass and it's still the same distance from the center of the Earth. It's just this force no longer equals the total force with it just sitting there. Okay. So hopefully I have warned you off of some of the more common mistakes that I see. So weight equals mass times gravity. Here's a quick one for you. It'll just take you a few moments, I think. Let's say you got a 500-gram object, assuming it's near the surface of the Earth, it's not on Mars or someplace. What does it weigh? Pause it. Now that you've hopefully figured out that that's, see, that would be 4.9 newtons. Where do I have that written out? Oh, yeah, over there. Writing it out in a little more detail than you might have bothered with. Weight is equal to mass times gravity. So about the only trick in this is the grams versus kilograms thing that I was talking about up here. You don't want to put in 500 grams. You have to convert that to 0.50 of a kilogram. People sometimes, oh, I can't remember. Do I move the decimal 2 places or 3? Well, as I've said before, the formula sheet is your friend. And right in the middle of a test, you get to use it. It says right there, kilo stands for 10 to the 3rd power. So that means you move the decimal 3 places. So 500 grams is 0.5 of a kilogram times 9.8 meters per second squared. You multiply the numbers, half of 9.8 is 4.9. As for the units, this unit times those units is kilograms times meters per second squared, if you want to write it that way. But as I explained earlier, that combination of units is given a name of its own. One thing I've never quite understood is, of course, this is a result of having taken drafting courses many years ago. They teach you to write in all capital letters, but if you use lowercase letters like normal people, in most cases, when you write out the whole name of the unit, it's written with a lowercase letter on the beginning. Even though it's a guy's name, when used as a unit, it's a lowercase n at the beginning of it. But the abbreviation is a capital N. That seems inconsistent to me, but well, it's just another case where, you know, nobody asked me. They just went ahead and did it. And so that's the way it is. Okay, so having rambled on for about 45 minutes about Newton's first and second law, let's return to the topic of vector addition, because I didn't quite finish dealing with that in section 2. And as I think I already mentioned, you need it here. It's the resultant of all the forces that's equal to m times a. So being, forces are vectors, you have to be able to do vector addition. So one way to find the resultant of, I guess I can leave that there a little longer. One way to find the resultant of a bunch of vectors is with the head to tail method on a scale drawing. And once in a while you might want to do it that way. But most often the more convenient and definitely more accurate way of doing it is to calculate it. I had you do some examples last week where you added some vectors mathematically. But, lay them out head to tail, and here's the resultant, and like you'd figure out how long that is with the Pythagorean theorem. Trouble is that only works if the vectors happen to be perpendicular, which most of the time they will not be. Most of the time, it'll be like that. Or worse yet, it won't be two vectors, it'll be 4 of them. There'll be another one there, and there'll be another one there, and then you have to draw the resultant like that. And yeah, good luck applying the Pythagorean theorem to something with 5 sides. So how do you do it mathematically instead of using, instead of drawing this diagram as a scale drawing? Well, a vector is in every way equivalent to the sum of its components. So like this one here, you can say, well, there's the y component and there's the x component, and do the components of this one and do the components of that one. You see, a vector is in every way equivalent to its 2 components acting together. So if you add up the components of a bunch of vectors, their resultant will be the same as the resultant of the original vectors that you started with before you found their components. And the thing about the x and y components is they are perpendicular. So you can use the Pythagorean theorem and all that good stuff. So that's kind of the thinking behind it. To kind of cook that down into a step-by-step recipe, to use the component method, first of all, you have to have components. So find the x and y components of each of the vectors you're adding. Hypotenuse times cosine equals the adjacent side, and so on. We've done several problems already where you have to do that. Then, once you've got all the components, add all the x's together, add all the y components together. Another thing that I use this for with alarming frequency is people forgetting or otherwise messing up their plus and minus signs. When you add things together, things that have opposite directions need to get opposite signs. The conventional way of doing it is anything to the right is positive, anything to the left is negative. Anything up is positive, anything down is negative. So when you add up all the x components, the total that you get is the x component of the resultant. When you add up all the y components, their total is the y component of the resultant. Now actually, giving the x and y components, well, let me just start into the next example, would be the thing to do at this point. Oh yes, and like it says at the top of the next page, sometimes page breaks just come at an unfortunate place, but it is probably impossible to draw too many pictures while you're doing this kind of thing. You need to be able to visualize what you're dealing with, And that's a nice piece of paper. I'm going to save that for something better than this. Put that over there with the printer paper. Okay. So for the lab, I'm pretty sure it's the third lab. For the lab that goes with this part of the course, what we have is a little metal ring and 3 spring scales calibrated in newtons pulling on it. And you're supposed to, you can read off the scales how many newtons each one is, and you can see which way the scales are pulling to get the direction, and you're supposed to find the resultant of those 3 forces. Well, for a classroom example, I simplified it down a little bit and made it 2 forces instead of 3. But that's kind of what's going on here. You've got whatever this is, maybe a little ring with a couple of strings tied to it or something like that. Somebody's pulling this string with a force of 100 newtons. Somebody else is pulling that string with a force of 150 newtons. Net force means what one single force would have the same effect on that ring as these 2 forces acting together. So works like this. From the steps on the bottom of the previous page, it said step 1 was to find the components. For this, I recommend a separate picture, at least for somebody who's just starting out, a separate picture for each force. There's the X and Y axes. And the one that I called force A pulls to the left like that. 100 newtons. The picture that comes with the original problem here, there's always people who think, well, this force is one of the components of that one or something. The way to approach any big problem is to break it up into a lot of little problems. And the little problem that you're working on at the moment is to find the components of this force. So I would put it on its own separate picture where you're not distracted by the other forces, and look at that and say, well, let's see, I guess the name of this one was A. So its X component is AX. And that's 100 newtons to the left. And since it goes straight to the left, it sits right on the x-axis. There isn't any up or down to it at all. AY is equal to 0. Moving on. The other force, sort of in that direction, 150 newtons, and we're told that this up here is a 10-degree angle. Well, once again, draw the little triangle. Hypotenuse times sine gives you the opposite side. So if this is, maybe I'll do it over on the side where there's a little more room to write. If that's the x component of force B, Bx is equal to 150 sine of 10 degrees. Now this may bother some people. You might look at that and go, hey, wait a minute. It's cosine that gives you the x component. Sine would be the y component. Not necessarily. What's always the case is that the sign gives you the opposite side of the triangle that you've drawn. Okay, this is the problem with just throwing numbers at formulas without really understanding what the formulas mean. It's like x equals hypotenuse times cosine, y equals hypotenuse times sine. Those are my formulas. I will drop the numbers into them, and I'm just being a robot and doing stuff like a computer would. And, well, if you absolutely insist that you have to use cosine to get the x component, then redraw the picture like this. Hypotenuse times cosine equals the adjacent side. Okay. See, the thing is, the sine of 10 degrees equals the cosine of 80 degrees. So you're going to get the same answer either way. To me, figuring out what this angle is just adds one more step to the problem. The question gave me this angle, I'll work with that angle. But, if you really want to do it this way, 90 minus 10 is not that hard to do. You're adding one more step to the solution, but it's not a very, I don't know if you heard that, fire engine. It's not a very big step, but anyhow, the reason I used sine up here is because it's the opposite side of the triangle. The 10 degrees is down here, the x component is over here. Sine is opposite over hypotenuse, so it gives you the opposite side of the triangle. Cosine is adjacent over hypotenuse, so it gives you the adjacent side of the triangle, which would be the y component in this case. And, you could do it this way if that's what you prefer. But as I've probably mentioned before, getting sine and cosine mixed up with each other is a fairly common mistake. I have definitely seen that one before. So be careful of that. The x component is the cosine if you're given an angle measured from the x-axis. If you're given an angle measured off the y-axis, then the y component is the cosine. Anyhow, you go ahead. Oh, I should also mention positive, positive, because the x component is to the right and the y component is up. If you were a bug crawling across the page who wanted to get from the tail of this arrow up to the pointy end, the bug has to go up and then to the right. So up is positive, right is positive. X component is 26. Y component, 148. Okay. So now we have the components of all the vectors. And, if the question had given you 73 forces to add instead of 2 of them, in a sense, it's not any harder because you just do this over and over and over again. It'd be harder in the sense of a lot more time consuming, but it's just repetitive, doing the same thing that I've just done here. So however many vectors there are, the next step is add the components. Well, one way of laying it out on the paper is like this. I won't always do it this way, variety is the spice of life, but Yeah, something's going on. There goes another emergency. Yeah, that one's an ambulance. Anyhow, sometimes maybe I'm a little too distractible. Some of the forces in the x direction. This is the math. Well, what it is originally, this is the Greek letter sigma. Sigma is a Greek S, S for some. Okay. Capital sigma, lowercase sigma. Sigma for summation. Add up the x's. Well, we've got two of them in this case. Summation of the x's means ax plus bx, which would be the negative 100, added to the positive 26. So I've got negative 74, measured in newtons. Similarly, summation of the forces in the y direction, that notation means to add up all the y components, ay plus by. Well, the one is just 0. And probably not worth writing out in this much detail, actually. But hopefully in the end, you had 148 newtons for that. Now, describing a vector by giving its components is a perfectly legitimate way of doing it. Basically, there are two different ways of describing a vector. You can tell somebody its magnitude and direction, the length of the arrow and which way it points, or you can tell them what its x and y components are. And a lot of times people do that because a lot of times it's more convenient. So if the question just simply said, find the resultant, if you got to where you could say x is this and y is that, well, that's the way this question is phrased. Find the net force. Well, the question phrased just exactly like that, you could stop at this point, and I'd have to consider that to be one version of the correct answer. But if the question was phrased a little differently, like this one I'm going to have you work on in a moment, find the magnitude and direction, well, then in that case, there would be one more step. So if the question's phrased in a way where you need to go on to find the magnitude and direction, draw another picture. People are always being skimpy with the pictures. Pictures don't cost you anything. The x component came out negative. That tells you that the x component points to the left. So you got 74 that way. The y component came out positive. So that one points up. So the vector whose magnitude I want to calculate is the resultant of its x and y components. To find the resultant of these two component vectors, draw them head to tail. Draw the resultant from where you started to where you ended up. Sometimes people want to reverse the direction for some reason. It goes from the tail of the first to the head of the last. And, let's use the letter R for resultant. I want to know how long that is. And I also, well, the conventional way of describing the direction is with an arrow, or is with an angle measured counterclockwise from the positive side of the x-axis, like that, okay? So the idea is it's 0 degrees is this way, 90 degrees is this way, 180 degrees, 270 degrees, and then 360 is the same thing as 0, okay? So ultimately, what you should give for the direction is this angle here. But the way I want to do it is I'm going to calculate this angle inside the triangle. We'll call that theta. And then I'll subtract it from 180 degrees to get this. But, well, we'll start out with the magnitude. It's a right triangle. So r equals the square root of 74. It's actually negative 74, but the minus sign disappears when you square it. So why bother writing it down? So you square, you add, you take the square root, and you should have gotten 165 for that. As for the direction, I like to, I mean, there's different ways of looking at it, but I like to work with acute angles. You know, I want an angle that's actually inside the triangle so that I can start with the definitions of the trig functions and figure things out based on that. The definition of the tangent is that it's the opposite over the adjacent. So you look at the picture you drew. Opposite side is 148. Adjacent side is 74. And that comes out pretty close to 2 even. So then you have to take the inverse tangent of that. Second function, you know, you put a 2 in your calculator and then do second function tangent, or maybe you do, it depends, the order you do it depends on the calculator. But if you can't get 63, actually 63.4 degrees from that, we should probably talk about how your calculator works. Well, if this was some test problem that you handed in to me, and you had written down exactly what I've got here, I would give you full credit for it, because I can look at the sketch you made and I can see, okay, 63 degrees is this angle over here, and so that would be correct. But if all you say is 165 newtons at 63 degrees, without any additional information to tell me something to the contrary, I'm going to assume you mean 63 degrees like that, which is wrong, okay? Like I said, the conventional way of describing things is that 63 degrees would be a first quadrant angle. If you're over in here somewhere, it should be more than 90 degrees. So to get this, 180 minus 63 is 117. Okay. So to tie it together into one neat little bundle, 165 newtons at 117 degrees is the answer. And that is how you add vectors with the component method, and that's going to be a significant chunk of lab number 3. So if you come in to do the lab, we can get, you know, some significant back and forth about that if you're having any trouble with it. If you're working from home, well, if you need help, maybe we can Zoom, or maybe I can work it out with emails or something like that. So how much more of this is there? well, it's a little early for the break. Let me just talk you through this next example, and then we'll take the break, which would normally be at 4:30 in the afternoon, but who knows what time it is where you are. So that's how to do vector addition using components. Now to actually apply it to F equals ma problems. Newton's second law, squeeze it in at the bottom here, that's a vector equation. You get the resultant of all the forces by doing this kind of thing here, and that resultant force is equal to the mass times the acceleration vector. A vector times a scalar is another vector. If the mass is 2, m times a is just a vector that points in the same direction as a, but it's twice as long if m equals 2. Anyhow, equality between this vector and that vector. If two vectors equal each other, that means they have to have the same components. If F is equal to ma, then the x component of the net force equals the x component of ma, and the y component of the net force equals the y component of ma. And what that does is it takes this equation that's about a bunch of arrows and makes it into two equations that are about numbers instead, okay? By separating it into x and y components, you make Newton's law into two scalar equations. Or if you're working in 3 dimensions, there would be a third equation, sum of the forces in the z direction equals m times az. An important special case of this is the case where the acceleration equals 0, which is what is happening in this next example. You handle it exactly the same way as you would if a equals any other number, but the reason it's an important special case is because it's used all the time in the design of structures, buildings and bridges and towers and things like that. You don't want to spend $100 million building a bridge by trial and error. It's like, oh, fell down. Guess we better use heavier steel next time. No, there isn't going to be a next time. I mean, it's going to be years before the lawyers are done with that one. So you need to figure out ahead of time exactly how strong each piece of that bridge needs to be, or whatever structure it is you're designing, so that you can make each piece the appropriate strength. And as sort of nobody stores bowling balls in their closet with a system of ropes like this. But if I gave you a more realistic example, how would you feel if I walked into class one day and said, okay, pick up your pencils, I want you to design the Brooklyn Bridge. Maybe better to have you work on a simpler example that involves the same basic principles, okay? So you've got a couple of bowling balls, 100 newtons each, and for some unstated reason, you want to hang them by this system of ropes. A couple of them attached to the ceiling, one attached to the wall over here. This one runs from the one ball to the other. And the question is, how strong should those ropes be? Well, if you're just hanging bowling balls in your closet, I guess you can just go down to Home Depot and buy the fattest ropes you see, and it's like, that ought to hold it. But that's not, if you're in a more serious design project, that's not the way to do it. Obviously, if you're just guessing how strong each rope needs to be, you're going to get in trouble if the ropes are too weak. What you might not appreciate offhand is that it's also a problem if you build something too strong, because strength usually equals cost, okay? If you're designing an airplane and it's like, Well, I'm not quite sure how strong each of this piece of this thing needs to be. I'll just build it real heavy, and that way there won't be any problems. Well, yeah, that plane's never going to crash because it's never going to get off the ground in the first place. Okay. Or even if you just overbuild it a little bit, each pound of metal you put in that airplane equals many gallons of fuel over the lifetime of that plane. That thing's going to be flying around for years and years. So the trick is to make it just as strong as it needs to be without getting carried away. Okay? And so before you even build your first prototype, what you need to do is figure out what the stresses on each part are. If you know how much, well, in the case of this, we're going to calculate the tension in each rope. The word tension means how much force is in that rope. Each little piece of the rope pulls on well, what does it come out? Number one, tension in rope one comes out a little over 75 newtons. That means each little chunk of this rope pulls on its neighbors with a force of 75 newtons. And at the ends, that's how hard the rope pulls on whatever it's attached to. So that's how much force is in the rope trying to pull it apart. And if the tension becomes too great, it will succeed. It'll pull the rope apart and your structure will fail. Okay? So usually they have some sort of a margin of error. If you're expecting 75 newtons, maybe a pick ropes that can take 100 or 130 or something like that, but no need to have a rope there that can stand up to 2,000 newtons. Okay, so the question is to calculate the tension in rope number one and rope number two. If I wanted to make the problem twice as long, there is certainly enough information here to calculate 3 and 4 also. But, well, you know, the class is supposed to end after 3 hours, so we'll just leave that part of it out and just calculate these two here. So, and again, if it's some sort of a dynamics problem where something is moving around instead of a statics problem where everything's just remaining at rest, you would approach the problem in exactly the same way. The only difference is that instead of the sum of the forces in the x direction equals 0 and the sum of the forces in the y direction equals 0, because they're just hanging there day after day, they're not accelerating. If you're talking about a rocket or something, then it's just acceleration is some other number is all. But you'd approach it the exact same way. So step one, create a free body diagram. A free body diagram shows just the object you will apply the equations to. Summation of the forces equals ma. Summation of the forces on what? Your first step is to answer that question. Well, if I'm trying to find force number one and force number two, they both pull on this lower ball here. Maybe I should be applying my equations to that ball. So you draw just the object under consideration, isolated from the rest of the world, just draw it by itself. The effect of the rest of the world on it is represented by arrows. Gravity pulls down. Rope number one pulls to the left. Rope number two pulls in this direction here, 53 degrees above the horizontal. Anytime you've got any kind of flexible cord, whether it's a rope or a chain or anything like that, a cable, the force is right along that cord. Now, this is not true if you've got like some sort of a rigid beam, okay? If these were all metal rods that had been attached to these balls by some sort of super epoxy or welded to them or something like that, then the force could be in any direction, because a solid rod can push to the side, okay? Not only that, a solid rod a string can only pull. It can only act in tension, never in compression. try and push on something with a string, and it doesn't work very well. You can only pull, okay? And you can't have any force to the side either. So because it's a flexible cord, it's a rope, we know this is at 53 degrees above the horizontal. If it was a rod firmly attached, you would not know the magnitude or the direction. So the free body diagram is a bookkeeping technique. It makes you take inventory of all the forces and show what directions they pull in and so on. Once you've identified all the forces acting on the body you're considering, the next step is to find the components of each force. And as I believe it says at the top of the next page, do not skip the diagram. I mean, people always want to jump into these problems here at step 3. They want to start writing down equations. Well, you know, if you've got enough insight that you can just picture the diagram in your head, well, that's wonderful. But I find that with many novices, probably most people who are just starting out, that is not the case. You want to take a big problem and break it down into lots of little problems, and that means having each problem laid out in a nice methodical way on paper so that you can focus in on just that part of it without looking at the rest. And then when you go on to the next part, the thing you calculated before is right there. And if you try and do everything in your head at the same time, it's going to get all mixed up and jumbled. And so don't skip the diagram. People who have no idea how to write the equations, I generally see that on their paper above the gibberish they've tried to put for equations, there is no diagram. So components. Well, this one acts right along the x-axis. It's got itself for an x component and 0 for the y component. And this one likewise pulls right down the y-axis, so there's really no work to do to get the components of that one either. The one that's on the slant is the main thing I need to work on in this step. Now, previously, we always had some sort of a number for what's on the hypotenuse. Like over here, it was 150 times the sine of 10 degrees and 150 times the cosine of 10 degrees. This time, we don't know how many newtons that is, so you have to pick a number. Well, I'm sorry, you have to pick a name to stand in for the number. I used T for tension, tension in rope 1, tension in rope 2. There's nothing sacred about using T. If you don't like subscripts, maybe you want to call it A and B, or I've always been sort of tempted to do a problem where just for the heck of it, I'd call the forces Fred and Alice, you know? I mean, just, you need a name is all. And if you've decided to call this force Alice, then Alice times the sine of 53 degrees is this side of the triangle, and Alice times the cosine is this side. Hypotenuse times sine is the opposite side, and so on. So see where people go wrong with this kind of thing is they do 100 times the sine of 53 and 100 times the 100 is this force down here. You don't know this force. If you knew that force, I mean, you'd be done, or well, half done. That's one of the answers the question asks for. So this is an unknown. The name has to stand in for the number until you're able to calculate the number. Once you've got the free body diagram, so here's how the equation comes from the picture. Sum of the forces in the x direction equals 0 because it's an object at rest remaining at rest, and therefore A equals 0. Every place there's a horizontal arrow on this picture, that becomes one of the terms in this summation. And some of the forces in the y direction, every place there's a vertical arrow on the picture, that's one of the terms in this summation. Okay, so the equations come from the picture. You know that the total has to be 0, otherwise the ball would begin to accelerate. Well, here we have an equation with 2 variables in it. Not going to solve that, at least not right now. Better to come over here, because this equation has only 1 variable in it, and so I can solve that. Top of the next page, I'm going to add 100 to both sides. Once I've done that, I'll divide both sides by the sine 53, and there it is. T2 comes out 125 newtons, which maybe I should point out, if you were going to try and just guess the answer, that's more than the ball it's supporting weighs. How do you get so much force? It's because the ropes not only pull back against gravity, they also pull against each other. Okay? So I think I said all of this. Every horizontal arrow becomes a term in that summation, and so on. Capital letters, probably I should have used boldface type and underlined it too. If you skip the diagram, you can't get the right equations, because the equations come from the diagram. Okay, all that's left, you know what, I might as well finish this. I should have taken the break a little sooner. I think I'm about an hour and a half in from where I started, but well, we probably would take the break in the middle of the class somewhere around here, but then I've got a lot of sample problems here for you to work on. Well, a lot, there's 3 of them. Maybe that's not a lot, but it takes a significant amount of time for me to stand there, give you time to think about, and then go over it, and then stand there some more and give you time to think about it, and the clock runs through all of that. And when I'm doing a video, the clock is not running. So considering I've just got a half a page left, I might as well just do the whole section 3 in this one video. And, you know, if you don't want to do the whole thing at once, that's one nice thing about a video. You don't have to. If you've got a short attention span, you can watch this stuff 20 minutes at a time, if that's what works for you. This first one is, I mean, there's no numbers in it. This is just an exercise in writing or in drawing the free body diagram. Okay, that kind of goes with all the capital letters up here. The diagram is important, so let's have some practice with creating the diagrams. So some of you maybe are familiar with the butter side down law. It's one of those basic laws of nature, like F equals ma. It says that if you drop a piece of toast, it always lands butter side down. It's one of the corollaries to Murphy's law. Anything that can go wrong will. So I actually read an article, I mean an actual semi-serious article where they proved the butter side down law. It was in one of my physics periodicals that I get a number of years ago. And what they did is they made some reasonable assumptions for how high the kitchen counter is off the floor, and how fast your hand was likely to be moving when it bumped into the toast. So you've got the here, if that's the kitchen counter, and here's the piece of toast sliding along. If you've got a reasonable estimate for the speed of the toast, as it goes off the end of the counter, it's going to kind of rotate like that. Once it's airborne, it's going to continue to rotate. So from the height of the counter and the speed the toast is sliding as it goes off the edge of the counter, they were able to determine, all the calculations were laid out there line by line, and they calculated that on the way down it would in fact turn roughly half a revolution, and they proved the butter side down law. So that's the background information for example number 3. So you pause it here, and now that you're back, I'll go over it. In Part A, while the collision is in progress. So I'm not gonna, well, you know, if it's a free body diagram of the toast, your hand does not belong in the picture anyhow. It should be just a picture of the toast, or if you want to get a little bit carried away, maybe show part of the kitchen counter under it. But there's the slice of toast. And you need to ask yourself, what are all the forces that act on this thing? Each one of them gets an arrow. Well, in pretty much any problem you ever do, there will be, maybe I should have drawn a thicker piece of toast so I had more space on it to draw arrows, but unless the problem deals with something floating around in outer space, there is going to be the object's weight. That's going to be pretty much always one of the things on your diagram. Now, gravity is pulling down on this piece of toast, but the piece of toast is not going downward. So something must be canceling out the downward pull of gravity. And that's the supporting force from the counter, the force that comes from being in contact with the counter. As we'll see in, I'm pretty sure it's section 4, the usual name for that is it's called the normal force. For reasons I'll explain next week. Furthermore, there is the force from you. It says the collision is in progress. So your hand is touching the toast and pushing on it. And it says in parentheses, it doesn't matter whether or not we've gotten far enough into this that the toast has begun to move. You know, because if you're really watching it like microsecond by microsecond, your hand, I don't know what I did with my box of staplers, so I'll play with the stapler, or staples, so I'll play with a stapler instead. Your hand comes into contact, if you're watching it in slow motion, your hand comes into contact with the toast, and as your hand continues to move, the force builds up. You press harder and harder, and it's going to be a few, it's going to be a little bit of a second, a small fraction of a second, before you're pushing hard enough that the toast begins to move. Well, whether the toast is still at rest or whether it's begun to slide, either way, there will be friction. Either static friction or kinetic friction. We'll talk about that in the not too distant future also. As the toast slides across the counter resists, it pushes back the other way. And there is the answer to Part A. 4 forces act on that piece of toast. Part B. Well, if you were completely clueless about Part A, maybe this has given you some direction. Part B is a little further along in the story. This is after it has bounced off of your hand. Your hand is no longer touching the toast. So if you weren't able to do Part B before, maybe pause it here and ask yourself What's different? What should I change about this diagram? And that little pause was for anybody who wanted to work on it a little more. Here's what's different. This force comes from contact with your hand. If you are not touching the toast anymore, that force is gone. So there's the kitchen counter. The toast is a little further to the right than it previously was, but nobody says I'm drawing the same part of the kitchen counter. As for the other three forces, the toast still weighs something, W for weight. The counter still pushes back up. That doesn't have anything to do with whether your hand is pushing or not. N for normal force. And as it slides along, friction still resists. Usually use a lowercase f for the friction force. So there's part B. Part C, after it goes over the edge, and now it's on the way down. It's a freely falling object heading toward the floor. Well, maybe it's begun to rotate, I suppose, if you wanted to. Maybe I should draw it like that. How the toast is oriented has really very little to do with the answer. The important thing is that this force, the normal force, and also the friction force, they both come from being in contact with the counter. Once it slides off and the thing is in midair, they are gone. So there's only one force left. Gravity pulling downward. It's a freely falling object. Okay, so that's the kind of thought process that you need to go through drawing these free body diagrams. Next question. I think, if I remember right, yeah, I'm sure. This was a problem I used on an exam a number of years ago. And when I wanted to have another sample problem to go over in class, I stole the problem off one of my old tests. So we've got somebody rappelling up an extremely vertical mountain. I mean, this person is well, it's not really a mountain at all. I think this is somebody going up the side of a building, basically. This might as well be a vertical sheet of glass. Got a rope attached to something up here. Of course, it goes down at a little bit of an angle to where her hands are. And the person who wrote I was trying to be nice to students on the exam. I basically did the free body diagram for them because I had all these arrows drawn on her. The contact between her feet and this wall creates a horizontal force. That would be the normal force again that I was talking about over here. And let's say that there's not enough friction at the moment to worry about any vertical force on her feet. Let's have a somewhat simpler problem. Let's just say that that's perfectly horizontal. The 600 newtons is what she weighs. That's right straight down. And the question is, what's the tension in the rope? The direction of that force would be along the rope. Okay, so try and sort of imitate what I did back here. I mean, really, it's not terribly different. You've got an unknown horizontal force. You've got an unknown horizontal force. You've got another unknown force that's to the right and up. You've got another unknown force that's to the right and up. Pulling straight down, you have the weight, which you do know. Pulling straight down, you've got the weight, which you do know. So this really is just this question all over again, just dressed up in a different suit of clothes, except I made it shorter. All I care about is this force. The one up here, you had to find both of them. You don't care about this force that's in the x direction, which would suggest that maybe you want to start with the y components. Anyhow, I may have said too much already. Here's where you should work on it if you haven't already. And here's where I come back after the pause to show you how I did it. And as I'm sure I've said before, if you were just completely stumped, after you've watched me do it, my advice is before going on to number 5, just pause it again. See if you can do number 4 yourself now. Okay. Free body diagram does not need to be a great work of art. You do not need to be Leonardo da Vinci. This is that lady on the side of the mountain, okay? And what are the forces acting on her? Well, they're all neatly laid out next, in the question in this case. I wasn't quite that nice to you in number 5. Number 5 just shows the situation without a bunch of labeled forces already drawn in. But she weighs 600 newtons. 600 newtons pointing right straight toward the center of the earth. Where her feet are against the side of the cliff, that creates a horizontal force, and I'm going to call it T for tension. You might want to call it R for rope, or F for force, or use your middle initial if you want. So anyhow, those 3 forces, that's the free body diagram. Next step, components. Well, just like in that earlier example, there really isn't any work involved in getting the components of this one or this one. For the rope tension, though, we have to draw the little triangle. And the angle that we're given in the question is this one up here. The hypotenuse is not 600 newtons. When I'm walking around the room looking over people's shoulders, I always see people trying to punch up 600 times the sine of 12 degrees and 600 times the cosine of 12 degrees. This force is the answer. If you know what this is, you're done. Okay? So this is not 600 newtons. This is unknown. The letter has to stand in for the number. Hypotenuse times the cosine equals the adjacent side of the triangle. And down here, hypotenuse times the sine would be the opposite side, but it turns out I'm not going to need that for anything, so I'm not going to bother to write it down. Summation of the forces in the y direction. I'd need this side of the triangle if I had to go on and find the force on her feet. But since the question only asks for the one force, I can get away with just writing the one. I try to ask reasonable questions on exams. Something that isn't going to take like 7 hours or something like that. Oh, wait a minute. Looking down the page at the wrong question. I just looked at my diagram instead of my cheat sheet that's off to the left of the camera, I'd have done a lot better. Every vertical arrow on the picture goes into the summation. Each term in the summation is one of the vertical arrows on the picture. So I've got t cosine of 12 degrees. That's up, so it's positive. 600 is down, so it's negative. Add 600 to both sides. Divide. And then you get out your calculator. And that's the tension in the rope. Okay, last one. So we've got a couple of acrobats on a tightrope here. And if it was just one person on the rope, these two angles would have to be equal to each other. But with the second person over here, they're kind of pushing the rope downward so that the angle is smaller on this side. As it mentions in parentheses, there would have to be an unknown friction force. If the rope was completely frictionless, this guy would fall off. But aside from that, if he managed to not fall off, he would slide. They would both slide downhill. The two people would kind of go and meet somewhere in the middle of the rope. It's not exactly true, but to a fairly good approximation, you can think of the friction force on this person's feet as being approximately horizontal. So in the x direction is a force that we don't know and don't particularly want to know, which suggests that the place to start is with the y components and see how far you get with that. So you need to draw a free body diagram of this person, get all the forces on it, and then do the components and try and solve for the tension in the rope, okay? The tension in the rope, we're going to say, is the same from one end to the other. That means that this section that's to the right of that person pulls in that direction with the same amount of force. And again, if you wanted to get really precise, this wouldn't be exactly true. There'd be a little bit of a difference because of this friction force, but to a decent approximation, this force is the same as the other side pulling the other way. So tension, that's the first sentence. Tension in the rope is the same from one end to the other. So based on that, see if you can come up with 3,600 and some newtons. And I might be able to fit it into that much space. Start with the diagram. Here is my malnourished looking acrobat. Forces. Well, if you aren't in outer space, there's always going to be the pull of gravity. And it says that he or she, whatever that is, pronouns are just getting so awkward these days. And you know, they is really a plural. It always doesn't feel right either. Maybe this person has multiple personality disorder. Then I'd be more comfortable using the word they. We'll look at it that way. So they weigh 700 newtons. And the section of rope on this side, I'm going to use the letter T for tension once again. Let's go to name as any. The rope on that side is 8 degrees above the horizontal. And over here, the part of the rope that's on the other side, that's 3 degrees above the horizontal. The picture is obviously not drawn to scale because the 3 degrees looks an awful lot like the 8 degrees. Question says it's the same force on each side. So you don't have to get into T1 and T2. They are equal to each other as far as we're concerned. And in addition, there would be a relatively small but somewhat significant friction force, which the question says we can consider horizontal. In reality, a few degrees off, but trying to keep it a relatively simple question. So as I think I said earlier, since it would be good not to have to figure out this force that the question doesn't ask us for, let's start with the y components where that force has no components. Well, gotta do the components here. Over here, this force has a y component of t sine of 8 degrees. Hypotenuse times sine equals the opposite side. Same idea over here. T sine of 3 degrees is the amount of upward pull in that section of rope over there. And then the x components almost cancel each other out, a little bit of a difference, which is equal to this friction force. Anyhow, every place there's a vertical arrow on the picture, that's one of the terms in this summation, which I sort of started writing up there because I wasn't paying attention to what I was doing. T sine of 3 degrees, that's that one. And then there's this arrow, also pulls up, so also positive. T sine of 8 degrees. This one pulls down, it gets a minus sign. Okay, that's where the physics is over, the rest is math. We have, we're supposed to solve this for t, that's what the question asks for. Well, combine the like terms. So the distributive property. T is a common factor. I factored it out. If you add the sine of 3 degrees plus the sine of 8 degrees, it comes out about 0.1915. And while I'm at it, let's add the 700 to both sides also. So added 700 to both sides and got a calculator and added these two things up, and they're equal to that. Finally, you divide. And what you see on your calculator looks something like that. We get to the end of this, and people always ask me, well, how was I supposed to know I had to have the answer in kilonewtons? Well, you didn't have to have the answer in kilonewtons. The reason I did it that way was so to round off to 3 significant figures. Okay, remember that whole thing about significant figures that I kind of glossed over a couple of weeks ago? Well, maybe you never quite got that figured out, but I feel I should try to be a good role model with that sort of thing just the same. So this was in newtons. And the problem is, if you want to round this off to 3 significant figures, well, let's see. This is just a little bit more than 55. It's just slightly closer to 60 than it, because there, there's a little bit of stuff beyond the decimal. It's a little closer to 60 than it is to 50, so it would round up. The problem is, if you hand this number to somebody, looking at it, they can't tell if that's good to 3 significant figures or 4. Okay? It is not, when you write it in this form, it is not clear if that 0 is significant. It might be there because you know it's 0, or it might be there just to show you where to put the decimal point. And it might actually, if you were, more precise about things, it might actually be a 5 or some other figure. So to avoid that ambiguity, let's 1, 2, 3 places over. Instead of writing 3, instead of that, we'll just say 3.66 thousand newtons. And when you write it like that, that clearly has 3 significant figures. Whereas if you had meant it to have 4 significant figures, you would have written it like that, because doing it this way, there is no possible reason for you to have put that 0 there, except for the fact that you know it's a 0. Whereas in this case, it might have just been to show you where the decimal goes. Well, of course, we don't know that it's a 0. What you had on your calculator was a 5. But the numbers weren't good to 4 significant figures anyhow, so we don't know that it's a 5 either. So anyhow, that's why I put it in kilonewtons rather than the newtons. And turn the page, and it says section 4, and that's a topic for another video. Have a good rest of your day. Or, if you're really into this, you can watch the next video now, probably. I'll probably record it later today.